Hello, we welcome you to Astro Adda. Today we have with us Dr. Ananda Hota. He'll be speaking on galaxy evolution through citizen science. And like we have been doing all these sessions, you can put up your questions, but please, Anand will take your questions after the end of the talk. So, but you are free to keep asking as we proceed. And before we commence, we'll introduce the speaker of the day. So here we have Priya. Priya.
Everyone, I'm Dr. Priya and welcome to everyone to Astro Adda today. Today our speaker is Dr. Ananda Hota. Anand is a professor leader at the UM-DAE Center for Excellence in Basic Sciences in Bombay, and he did his PhD in the year 2006 with the IIC JAC program and NCRA. And after that, he had postdocs at Ayuka, at NCRA, at Taipei in Taiwan. One of his major jobs that he's been busy with is the Lab at Home. And Lab at Home is a citizen science project that he's been doing. His interests are multi-wavelength, ultraviolet, optical, infrared radio data of black hole galaxy coevolution cosmic wave. And he has been very encouraging to a very large population of students who have been working with that at home. And I think it will be very beneficial for you to talk today on that at home and how students can contribute in this citizen science project endeavor of this. So I welcome you, Anand, and look forward to hearing you.
Yeah, Anand.
Yes. Hello, everybody. This is my first YouTube live talk.
Yeah,
so
Anand.
it's yes. So it is very interesting. Hello, everybody. This is my first YouTube live talk. So it's yes. So it is very interesting. Let the echoes die down. I'm waiting for that. Let the echoes die down. I'm waiting for that. Hello. Okay. I hope we can start. Hello. Okay. I hope we can start. I'm hearing back my own voice again and again. I'm hearing back my own voice again and again. I don't know. Okay, let's move. I don't know. Okay, let's move. This is one of probably my second cover page of my talk. The first one is the declaration that you all know. This is one of probably my second cover page of my talk. The first one is the declaration that you all know. The first one is the declaration that you all know. Is all okay? Is all okay? Hello. I think it's okay. I'm not listening my echo now. Okay. Um, let's move. Okay. So this is my first talk live, and now we will move regular as normal expected. This is a packed slide in some sense. The title is a bit also long. Galaxy evolution through citizen science research using Red at Home and GMRT telescope. My name is Ananda Hota. I'm a UGC faculty in UM-DAE Center for Excellence in Basic Science, Mumbai. You can know more about me in the link given here. On the left-hand side, you see this big India map and one of the discs of GMRT and a lot of institutional logos given there. These are the various institutions, roughly almost 2 dozen. They are supporting this citizen science efforts. So why this is important, why these people, so many institutions are supporting, we'll talk about this. And the middle picture, discovery of an exotic galaxy speca. This is what I have led in doing it. And there are many collaborators, obviously. Science research is done in a collaborative way. We'll talk about this. The other one also you may have seen in Bigyan Samagan and SCA telescope brochure. Another discovery led by me. And the last one here is the first image of the black hole by the Event Horizon Telescope group. So all the radio telescope is observing is mostly plasma emitted by galaxies having a black hole at the center. So bottom line of this talk is how we will use GMRT in a nationwide inter-university citizen science program, how you can contribute to the black hole galaxy evolution studies, and grow together in your understanding as well as in your career. Okay. So outline of my talk is we'll have a look at what is this topic through Wikipedia, through Google's view, very quickly, and then go a bit more detail on galaxy evolution. Okay. Then, why do citizen science research (CSR) with Red at Home using GMRT and in future with SCA? We will discuss a bit more detail. How students and university science educated citizens can participate in Red at Home. I will describe this step by step ways. Then few success stories of few students, few citizens in their career, their understanding of science through citizen science that I will describe at the end. And then we will go for question and answer. So the quick, as I said, this is what is the article in Wikipedia on galaxy evolution. There is an article titled Galaxy Formation and Evolution. You can see galaxy formation is more like cosmology. Evolution is also from cosmological, that CMBR picture, how galaxies are evolving till today. Commonly used observed properties of galaxies that will describe how black holes property and the galaxy's properties are correlated, how their structure, color, dynamics, star formation history, black hole activity are correlated. So the subsection of that Wikipedia article is galaxy mergers and formation of elliptical galaxies. You all know stars form in a galaxy like Milky Way galaxy's neighbor, small Magellanic Cloud and large Magellanic Cloud. Lot of star formation happening, like happening in the belt region of Orion constellation. Galaxies merge, interact. When they are merging, they're forming a lot of stars. And the other type of galaxies, apart from this merging and spiral galaxy which form stars, are elliptical, which don't form stars. So this topic is called Galaxyquenching. So this is the bottom line of the galaxy evolution picture. They merge, they form star in the beginning. Spiral galaxies mostly form star, they merge, they get quenched. And at the end, they become elliptical galaxy without star formation. And this is what we are trying to understand. So let's come to the second half of the topic of the title, Citizen science. What is citizen science? Wikipedia defines this way, that how public participate in the science research process. Volunteer monitoring, online citizen science, crowdsourced science, public participation in research, various names are there. And among them, the most famous ones are iNaturalist, eBird, Juniverse, etc. Juniverse, let's come. This is now almost more than 2 million members probably. By March 2019, it was 1.6 million. Now it has probably close to 2 million. The very famous. It has many astronomy projects as well. So, if we search citizen science, astronomy, and India in Google, what do you get? This is the picture. So, we are not only the first one that we are claiming, we are probably the most important one. So, square kilometer array, like the bigger than GMRT, that is, many countries are participating. The country flags you can see to build the next generation largest radio telescope. During this COVID-19 or coronavirus pandemic, they advised public to participate in various citizen science projects so that people can learn from home. So citizen science research projects they advised to participate are few of them are listed here. I'm quoting screenshot from their website, scartelescope.org. Einstein at Home, Radio Galaxy Zoo, Radio Jove, Gravity Spy, and here comes the Red at Home. Juniverse as well as AstroQuest they have added. So here you can see the group photo of one of our Red at Home's Discovery Camp training program held in Nehru Planetarium, Delhi, which is hosting this talk. So as the website details, Red at Home is Real Astronomy Discovery at Home is a citizen science project aimed at undergraduate students mostly in India to work on understanding black hole galaxy evolution mainly using GMRT, one of the SCA pathfinders officially recognized as. GMRT is a SCA pathfinder. Understanding or the technological development, that scientific development that we achieve through GMRT will be leading to the SCA development, which is the telescope being planned, is yet to be built. The project aims to prove that any BSc, BE, BTech, undergraduate or graduate can do multi-wavelength extragalactic astronomy research. This is the first Indian citizen science research program in astronomy. So the picture that you have already described in the cover page will elaborate all these things. Okay, so why GMRT, why Red at Home? Anybody is going to ask naturally. GMRT, largest such array disk interferometer, largest such radio telescope in the world. Other telescope may be there in some different parameter, they may be bigger or smaller, but this kind of disk array, synthesis array, aperture synthesis array, so many disks looking at this same part of the sky, rotating and tracking the sources, this is the largest, and this is the pride of the nation. Thus, we should use this. And the GMRT, that the survey of the all sky that it has created, it is called TGSS, TFR GMRT Sky Survey. That TGSS survey, you can see the bottom plot here. This is resolution, this is sensitivity. So RMS noise which is less is better. Resolution which is high or this value is low is actually better, sharper picture. So TGSS here is the smallest resolution or sharpest picture, lowest frequency. There is nothing here. So TGSS survey images that you see, that GMRT has imaged all part of the sky, almost 90%, whatever is visible to it. And the images it has created is the highest resolution, low frequency sky survey. That is why if we focus the sky with this best quality data, we can definitely discover many things. That was the bottom line of starting a citizen science project from India. That is Red at Home. Okay, where do you fit in Red at Home? People easily ask that you fit at the bottom because I'm addressing to involve largest number of people there. RGB image, red, green, blue color image making people. And then once you are doing well, you will be trained for 7 days in the camp that I described, Nehru Planetarium, Red at Home Discovery Camp, in that kind of camps. There are 150 of them trained over last 6 years. Then there are leading members who are participating in the designing of this discovery, because student teacher kind of put designing it together. Then I am there as the principal investigator of this collaboratory. And the people who have been helping us, like Dr. Ratnasri, who is the director of the Nehru Planetarium, they are here, institutional facilitator. 24 institutions are supporting this citizen science collaboratory, I said. The leaders from those institutions are the wing. And the professional collaborators who are collaborating in the GMRT data analysis, GMRT data discovery of those objects, helping you to publish those papers. Those real research collaborators, they are together helping all of you going to fly this huge pyramid. That is how hierarchically everybody gets involved in making publications using GMRT. So bottom line in one slide, how do you participate in Red at Home is this way. I teach from home. It communicates through the internet, through Facebook chat, and students sitting at home, they learn. Once they discover looking at TGSS data from GMRT, we propose to GMRT something called GMRT observation of objects discovered by Red at Home Astronomical Laboratory. We get GMRT telescope observation time, and tiny, small, faint, fuzzy thing that you have seen and found, we are suspecting something new you have seen, that will be detailed imaged. Something like you have seen what it looks like 5 minute exposure, and we will go for 5-hour exposure with GMRT. You can imagine a mobile camera photograph and a DSLR photograph. Lot more detail can be figured out. That is what institutions are supporting. Okay, and you will become a co-author in the discovery paper because you have discovered it. Okay. So typical citizen science research solves problem of the big data, so much data the telescopes and computers are producing. Red at Home tries to solve same big data problem, but in a different way, but also solve the geopolitical, socio-economic problem through interactive or collaborative citizen science research, so that you actually participate in growing your own career. Thus, SCA and the 30-meter telescope, like mega science, brings a big prospect because so much of data is coming for you to learn and discover and grow in your career. Typically, everybody thinks astronomy is this, like layman picture. So buy a toy telescope, enjoy night sky, stay inspired. I have done this. I was doing this. But to do research, those telescopes are not enough. You have to win or own data in world-class research telescopes, big observatories, make discoveries, inspire others. You cannot own this kind of telescope. No single country is able to make this kind of big telescopes now. That's why for SCA and TMT, so many countries are coming together. Be part of Red at Home, be part of this project, and let's grow. So astronomy, everybody is fascinated about this thing, that there is CMB, cosmic microwave background radiation, soon after the Big Bang. You see the picture, and then you come to the sky, beyond your constellations and stars, you see galaxies of different shape, different dynamics, different structure, different color, different evolutionary history. So how from this seed distribution, like CMB picture, this kind of big galaxy like trees have grown in a different kind of trees. And that is our understanding now. That is what we are going to understand. From Big Bang picture to CMB to galaxies, black holes, planets, star formation, ultimately probably life, but that is not a subject of Red at Home. So you all know this is a pretty wonderful HST picture, Hubble Space Telescope picture, spiral galaxies, elliptical galaxies. See the color and structure differences. They are telling you something. Their dynamical history is different. Their gas content is different. Their color of the stars are different. They have different evolutionary history. And some of the galaxies are merging, interacting purely by gravitational force, and something star formation is also increasing. So galaxies are not static. The way the snapshot picture shows, they are not static. They are accreting, rotating, evolving system with star formation and AGN activity, black hole activity basically. When black hole reads matter, active electric nuclei, AGN they are called. Let's see a quickly a simulation, just less than 2 minutes. Okay, see this picture. This is simulation mathematically produced, obeying all physical laws. Small clumps like LMC and SMC, how they are merging and growing a bigger galaxy. They are merging because the gravitational pull, they get attracted, they overshoot, and they come back again. This is how our galaxy is actually. The spiral structure, you can see now that they are forming. You may ask, okay, I see this spiral structure in spiral galaxies, but what are this so much of fuzzy thing all around? Yes, that is also seen. That is also seen in the gas. H1 gas like radio telescope detect. Go in Google, I can show you sometime. That the pink layer-like thing, there start forming spiral arms. The faint bluish green that you see cyan-like color, there is the gas there. Neutral atomic hydrogen gas emitting in 21 centimeter spectral line. One can see huge disk of rotating gas. This kind of a merge, like Andromeda and our Milky Way galaxy will merge. Okay, like this is what is going to happen in future. This is what galaxies are, dynamical system. They are not static. So unless you develop this dynamical understanding from looking at simulation pictures, you will not be able to understand the static RG, red, green, blue, or multi-wavelength picture at all. So let's go back. Okay. So this is what is the deep picture. Okay, a deep picture of the sky. A very almost blank part where there is no star there. Picture has been taken, and in that no stars are there. When you look for days long with Hubble telescope, best angular resolution, because there is no atmosphere, there is no seeing, you can say, or twinkling, you can say. You can see so many galaxies. They are at different distance. Light has taken different time to reach us. So universe at a different epoch, different age, you are seeing all together in the same picture. They have been compressed, you can say. So galaxies are at a different distance, they are at different dynamical distributions. Some are in groups, some are isolated, some are elliptical, some are spiral. If you want to see them in different distance, let's go through once again. From the Millennium simulation, the galaxy's formation evolution has been created by Millennium simulation group, and let's see how the galaxies are distributed. This is another simulation picture. This is not animation, there is no art, this is science part. The point, the location, the brightness, the size, everything is actually mathematically created following different physical, like hydrodynamical law, Newton's law of gravity, etc. So you can see that the galaxies are distributed kind of a network of road-like thing. At the center, this is like a metro city. Small highways, you can say. Smaller towns along the highways. They are all connected. Many national highways are connected to the metro cities. So these metro cities, cosmic metropolitan city, these are called clusters of galaxies. Every pixel here, every spot that you see here, every blob that you see here is a galaxy. These are clusters of galaxies. There are thousands of galaxies there. They are all bound by their common gravitational pull. Everybody is going around the center. It is a fly through. That is why you are seeing them. The rotation that you see here is not dynamical rotation, but the point of view or the viewing angle is getting rotated. Otherwise, like solar system thing, they will be going in an elliptical orbit always. So let's not spend much time. So galaxies are distributed in this kind of cosmic web, clusters, groups. These are like groups. They are falling towards the cluster. This is how things are. Okay, let's come back. So how this is happening? That far away galaxies and nearby galaxies, they are all put together. In this Hubble deep field, if you see far away galaxy, how they will look like? They are at shift 7, at shift 8. That means light has taken several billions of years, 10, 13 billion of years almost. So the small few galaxies that you are seeing in blue light here, they are formed after 500 700 million years after the Big Bang. The first billion year of after the Big Bang, first billion of our universe. Compared to this thing, compare the O and A type star, or few million year survival time on. So what do you do with looking at so many galaxies there? First thing is sort them out with distance, what type they are. Okay. So nearby universe, redshift 0, nearby universe, almost all galaxies are falling into two mode, elliptical and spiral. Okay. But if you go back in time, redshift 0.5 or 9 billion years after the Big Bang, redshift 1 or roughly 5 billion after the Big Bang, redshift 3.5, 2 billion after the Big Bang, how the galaxies were looking. Gradually, you can see from left to right that galaxies are no longer falling into the standard spiral or elliptical structure. In their formative era, they are actually ill-defined structure, dynamically unstable state. They are yet to decide almost which category to fall into spiral or elliptical. This basic difference of spiral or elliptical doesn't exist in the high redshift or early universe. So what else? You can understand there at what rate they are forming star. Our Milky Way galaxy forms like one solar mass amount of star per year, roughly one new star forming every year. You can see, and roughly in a 10 year, one supernova explosion happen. Okay, so here is the plot. Okay, observationally derived. Here is the plot. Bottom is the redshift. Top is the look back time. Big Bang here, and we are observing the star formation rate per unit volume, million solar mass per year per megaparsec cube. The famous Madhav plot. The star formation rate or rate of star formation is low currently. It was high roughly 10 billion year ago, redshift 2, and it was lower closer to Big Bang again. So the star formation rate of our universe has slowly increased and then decreased. So this point, midpoint, peak point, can sometimes be called cosmic noon. So what happened that since this cosmic noon, that the star formation in galaxies overall in our universe has been declining. I told you before that very early there were not so defined galaxies. They were not neither spiral nor elliptical. And now that most of them are either spiral or elliptical. Spirals mostly form star, and elliptical don't form star. But overall in our universe, this is the star formation history, cosmic star formation history. How this is happening and why this is happening. This picture, very early, redshift 18 or 200 million after the Big Bang, sky was almost like uniform gas distribution. Slowly, it increased and the contrast. Gas from the outskirts get merged towards the clusters. Notice here. This is what is actually happening. Okay. Let's quickly see in a movie. You can see here how uniformly, almost uniformly, after CMBR, this is about the gas distribution. Slowly, left hand top, you can see here, you can see redshift. Right hand side, you can see the time since Big Bang. Okay, 100 million after Big Bang. So slowly, the contrast is increasing. Voids, large empty region is created surrounding region. And then at the central region, where the gravity is higher, where the density was high, it was hot, it was cooling faster. When it was cooling, the gravity is superseding, is overtaking, and things are falling towards the center at a faster rate. And this is how the clusters are forming there, the metropolitan cities of our universe forming there. Small groups, they will merge to form bigger clusters. See how it is growing with time. 700 million years after the Big Bang. This is how the groups of galaxies, clusters of galaxies are forming now. And it is a continuous process. In this evolutionary process, shape of the galaxy, star formation history, they all are slowly changing. So what physical processes that has been going through, the galaxies have been going through, that they are changing. This is what is the cosmic evolution of galaxies and their black hole activity. See how things are evolving. Okay, currently we are redshift 1. Let's speed up a little bit. So different color is because of different star formation rate there, different amount of gas there. So gas and stars are all put together in this simulation. All these things will be there in YouTube, so you all can watch again and think through these things. Okay. So currently this 12 billion years after the Big Bang, almost we are going to a nearby universe. The cluster will have a central brightest cluster galaxy at the center, and that is all so many stars surrounding, so many galaxies surrounding them. So the gas and galaxies are coming towards, converging towards the center of the clusters. So there is one more point here, that you have seen the galaxies, their brightness and their color. So how astronomers determine color of a galaxy is like they take the measurement of the galaxy's brightness in one filter, say in green filter, and the other measurement is say in your infrared filter, say infrared filter. So G minus I, G minus I, y-axis you can see G minus I magnitude or color of the galaxy. And then x-axis you can see the mass of the galaxy in some sense. So here the mass is high, right side, mass is increasing in x-axis, and the color, red color is actually increasing in the y-axis. Or as the color code says, here the galaxies are looking optically blue in color, real color, optically blue. And here in the elongated region, they are actually looking reddish. Here, most of the galaxies are elliptical. Here, most of the galaxies are spiral. When they are forming stars currently, O and B type stars, that will be looking blue. So that is the point, that most of the galaxies in our universe are falling either into this blue cloud category or into the red sequence category. Very few fall in the middle. Okay, as the galaxies are probably merging, as you see in the simulation, two spiral galaxies merge, they grow in mass, they should grow in mass straight from the right side, but they don't do that. They don't move that way. Somehow they merge and evolve towards a not star forming galaxy. That's how they become red in color. So why is this happening? This is a big puzzle. Why this is happening? For example, let me give you an analogy. Why this is a puzzle? Say on the y-axis you plot the height of a person, and the x-axis you plot the weight of a person. If the person is growing, it will be a smooth migration in the plot. For some reason, suppose the person's height doesn't grow, but the mass continues to grow. So the movement will be different. For some reason, say in coronavirus, they eat more and gain more weight. Their height doesn't grow that much, but the mass grow too much. No physical activity. Lockdown at home. So the galaxies' growth in their mass and star formation rate is depicted in this color and magnitude plot, so-called color magnitude diagram. So why they are missing in the middle part, some people call it green valley, it is an important question to understand. If the galaxies merge and become a bigger in mass, why does the star formation stops there so that they become red? The bigger giant elliptical galaxies has more gravitational pull. It should be pulling more gas from the surrounding, like you have seen in the simulation of a Milky Way galaxy there. It should be forming more star. It doesn't happen. Why doesn't it happen? It's an important question that we're trying to understand. So bottom line from the Wikipedia picture here, at the left-hand side, this galaxies, thin galaxies, they form star, they look blue, and probably it migrates, and they become elliptical galaxies with big bulge and thin disk there, and they no longer form star, they become red in color. Some people call it red and dead galaxies. Okay, they have a lot of story to tell them. Another puzzling thing is very interesting. Left hand, the x-axis is showing you the mass of the central bulge component, the spherical part of the galaxy. And the y-axis is mass of the black hole. The famously known M sigma relation. What it means that the bulge part, the spherical part, its mass, its brightness, its velocity dispersion, everything is correlated, tightly correlated with the mass of the black hole, supermassive black hole at the center. For example, suppose the star formation continues and the galaxy grows in mass, it should move this way. No, it doesn't move this way. It has to move in a correlated way or hand in hand way with the mass of the black hole. So when the stars are forming and the galaxy is growing, somehow the black hole is also growing. Suppose the black hole grows a bit high, stars don't grow. Something will happen that the galaxy has to grow. No one grows without any coordination. So to understand this puzzle, color magnitude change, color magnitude diagram, as the M sigma relation, people did simulation. What happens during a merger? This is famously again from the Millennium Simulation Group. And what is showing here, when the two spiral galaxies rich with star formation, a lot of gas merge, they form tidal tail, etc., etc. That disturbance, tidal effect, creates gas to fall inside, and that creates a lot of stellar wind, O and B type stuff. Lot of star formation happens, and then the galaxies merge, and it blow away the solar wind. Like solar wind we have, there is still O and B type stars create that kind of wind. Let me ask everything is okay. Okay, so by the time this merger process is over, two galaxies merge and become a merger remnant, one single galaxy. Lot of gas has been thrown out by the supernova explosion, stellar wind, etc., etc., and the accretion onto the black hole that create a lot of radiation pressure that also blows away. Okay, this is what is an puzzling thing. Let's see quickly in a simulation by the same group. See this, two galaxies are merging. They're forming tidal tail. The pink thing is showing now they're forming a lot of star, hot gas there. So roughly look at the left-hand top part. 600 million year, 700 million year. So roughly in a billion year time scale, the galaxies are going to merge and become roughly in a 2 billion time scale. So this green thing that is blowing away, this is the wind that is blowing away from the center. Before the merger also, this kind of blowing away happened. After the two nuclei merge, also this switch continue. So by the time the merger remnant become a single picture, single galaxy, it is not left with much gas to continue forming star. Very little gas is left. So that is what happens, that at the end, the remnant of two spiral galaxies merging, has been left with a gas poor, no star formation, red and red elliptical galaxy. They no longer have gas left, been blown away, etc. Okay. So there is another something called luminosity function. Okay. Here, the number of galaxies you observe in a part of the sky with luminosity L to L plus del L, and here the luminosity. What you observe is that because of this merger process, a particular theoretically expected shape is expected. That there will be small luminosity, large number of sources, and the merger process is continuing. So by merger process, the big galaxies, bright galaxies are forming, their number will be less. What is observed is the blue line. Theory is the red line. Observation is the blue line. There is a mismatch at the lower as well as higher end. That is what is being now explained by this kind of wind outflow process, something called quasar or black hole or AGN feedback. This quasar or AGN or black hole at the center is giving a feedback to the galaxy how it should grow in the star formation process and mass and light color process. So in this particular big picture, unified picture, you can see here that the single galaxy isolated disk, small group, galaxy merger. When they merge, they blow away gas. Lot of ionized gas and hot gas blown away goes out of the galaxy. You can see the quasar at the center, very bright, brighter than the galaxy itself. Quasars are seen, and at the end, post-starburst phase, K plus A galaxy post-starburst phase, there is star formation has been over in it's not happening, and finally nothing happens. Basically, a dead elliptical galaxy forms. Here you can see the star formation rate, bolometric luminosity of the quasar component. You can see how it grows because of interaction and dies. How it grows because of interaction and dies. These are observation and theoretical expectations. So hierarchical growth picture is galaxy formation and evolution is at the central topic. Hierarchical growth means galaxies merge and become big one. Gas flows in because of accretion, star formation happens and the quasar becomes bright. By this accretion process onto the black holes grow, they become active. The radiation and wind feedback blows away the gas. Because of less gas, the same thing happens. That they become normal galaxy again. Nothing happening there. So dead quasar. The normal galaxy which had a quasar some time back or active quasar. And same thing happens, it continues to accrete again and then grow. So these are probably a loop process that continues. So the bottom line in this picture is there are red and dead elliptical like galaxies on the right hand side. There is product, dead galaxies, and something has killed the star formation story in that. Can the black hole be the culprit that it has killed the star formation story of a galaxy? Okay, if that is so, can we find a smoking gun evidence that AGN or the black hole's accretion did this? Nobody has seen that kind of smoking gun evidence yet. What do I mean? Is that people have seen the bullet has power, people have seen the gun firing bullets, people have seen dead galaxies, dead bodies, but they have not seen a gun with smoke that has the time scale compatible with the time scale since when the star formation process is dead in a galaxy. Got my point? The smoke cooling time scale can be estimated. When the person is dead, can be estimated. Same thing we do. We see the smoke part or the plasma part or ionized gas part that the AGN create, the black hole or the quasar create. We can get their time scale. You can get the time scale of star formation, how many years back this galaxy star formation process mostly got over. Okay. This is a lady who became very famous, citizen scientist, school teacher. Simply asked, what is this green looking fuzzy stuff there in a galaxy picture? Citizen science process that the John Hopkins University, Oxford University, and many other universities and institutions started around in 2007. So she did not know what is this. Neither she actually knew, nor any scientist actually knew at that time that what is this green looking fuzzy stuff. It's not looking like a galaxy, not looking like a star. What is this? Why this is not seen in red filter? Why not this is not seen in blue filter? It's looking only in one filter, one color. This lady Van Erkel, once he asked this and a lot of people discussed this, people did not know, so they started following up with Chandra telescope, radio telescope, Hubble Space Telescope, everything to understand what is this fuzzy looking object. So her contribution has an analogy. That is a small by asking this simple question. She has no astronomy background. Small but a significant role of citizen scientist. She became co-author of the discovery paper. Scientists did follow up with Hubble Space Telescope, but she was a co-author there. Important contribution. Our mythology, Ramayana has this kind of story. I'm just keeping you. You can read. You must be knowing and can read it somewhere else. That when monkeys were doing the big heavy stone lifting and building the bridge, squirrel was doing the small task. Okay, let me not go through. Citizen scientist who discovers, though their understanding may be poor or less advanced of what they discover, because without their help, one astronomers cannot discover from the big, huge amount of data from telescopes, build with their taxpayers' money actually, that cannot be discovered, so they deserve a credit. That is what is the bottom line of a citizen science discovery process. This is what is that this lady's discovery. That when this big spiral galaxy had an active quasar in it, it had ionized gas and it is glowing still now. The process is the Wikipedia picture. There was a galaxy which is going around the big one. It left gas trail as it flows, and that quasar's radiation actually ionized this thing, and it becomes burning or glowing. The electron jumped up, it was radiating spectral line. It was giving spectral line, that is why it is not seen in every filter, but only in that small wavelength range. So the point here is, after a while, the accretion process onto the black hole stops and the quasar is dead. It is no longer bright to be seen as a quasar. But the burning gas, the ionized gas, hot gas, is actually slowly cooling at a certain rate. So at that right moment, astronomers have seen this, that this is a burning, glowing, colored gas cloud, fuzzy looking, faint thing. We followed up with other telescope. So let's look at the elliptical galaxy and spiral galaxy. When you take a spectrum, you get a lot of spectral line emission from star forming galaxy. You don't get that kind of spectral line, bright emission line from red and dead elliptical galaxy. This is what, looking at the emission line or absorption line, one can figure out what kind of stars are there in the sky. Looking at their color, one can figure out what kind of stars are there in the galaxy. So this is OBF FGKM star color emission line, absorption line profile that you all know. Roughly same thing happens with the galaxy also. Galaxy which is roughly like 100 billion stars in the galaxy. If you observe a galaxy's brightness in UV, optical, IR, different band, you observe at different bright filters how bright they are, and try to fit this curve, star population synthesis curve. What curve fits them? If it fits to the lavender violet color, most of the stars in the galaxy are basically few million years old. If it fits to the red one, most of the stars in the galaxy are actually several 10 billion years old, several to 10 billion years old. If it fits in the yellow-like thing, it is probably like sun-like thing. They're like 4-5 billion year old stars. So a spiral galaxy will be of this kind of nature. The most of the stars will be young there, and elliptical galaxy will be most of the stars will be old there. So looking at color of the galaxies or looking at spectrum in different wavelength band, one can determine how old the stars are there, or otherwise, since when new stars are not forming there and there are only old stars. That is what we want to understand now. Since when the star formation in the galaxy has stopped. So looking at this Hani's object, the quasar echo, one can figure out that citizen scientists found actually many more, dozen more such objects. Once they were asked that Hani is famous and there is an important thing that astronomers don't know what are they are studying, they found many more. And those kind of objects are few 10,000 year old systems. The plasma there, the galaxy's quasar, was dead some 10,000, 20,000 years ago. So you can tell the quasar or black hole archaeology up to 10,000, 20,000 years ago. But interestingly, In radio mode, if you want to observe radio plasma from this kind of black hole system, quasar system, one can go hundreds of million year old, several 100 million year old plasma. So one have a better tool now to understand the smoking gun evidence, how much back in time one can go. So post-merger, post-starburst galaxies with radio mode, one can go much back in time. Black hole archaeology, people call it. So let's see actually what radio plasma sees in a galaxy. This giant elliptical galaxy at the center, optical picture. This is like a Milky Way galaxy, small one. You can imagine now how much mass is there in the giant elliptical galaxy. Our Milky Way like galaxy, our galaxy has a few million year solar mass, black hole at the center. And this galaxy will be a several billion year mass, billion times mass for our own sun, the black hole's mass. So the pink looking thing, this smoke plasma that you see there is imaged by radio telescope VLA. And the optical picture that you see, real color picture there in the background, is the HST picture. What you see here? You see here the giant elliptical galaxy has ejected out big two plasma blobs. And these big two plasma blobs will be seen exclusively in the radio telescope images. You don't see in optical. You don't see in, there is no atom, there is no molecule. There is no atom, there is no molecule. There is no spectral line coming from these blobs. There's no thermal plasma there almost. It's only non-thermal plasma. I will come to this later. It's another picture, Cygnus A. Optical galaxy at the center, looks like disturbed. And the plasma seen in, radio plasma seen in red from VLA again. This is another optical picture, same Cygnus A, radio picture in red, and the X-ray picture from Chandra X-ray telescope is seen in blue. What you see? The galaxy's stars are actually at the center, and the thermal plasma, million degree Kelvin hot thermal plasma emitting X-ray is surrounding that thing, blue looking thing. And the non-thermal plasma, relativistic magnetized plasma coming out from the center, like two blob, is somewhere else. Red is the non-thermal plasma, blue is the thermal plasma. Galaxy is surrounded by this kind of exotic things happening, not completely empty. This coming from the central galaxy. The star-like thing, galaxy-like thing are the foreground or background. They are not connected to this. Okay, so with our GMRT, we see this kind of plasma coming out of galaxy's black hole system at the center. With this kind of thing, as I told you in the beginning, we discover this kind of exotic galaxies, understand how this plasma coming out of black hole affect the star formation in the galaxy, what is the reason, what is happening from there. If I'm able to lead that kind of understanding and study, I want to involve you in participating in that kind of research with GMRT, wherever you are. So to do that, let's have a quick understanding of how this plasma jet is coming out. We really don't understand how this is coming out, but let's take lead from the simulation studies. Okay, this is our first black hole image, MIT-7, that study. So while it is loading, this is the MIT-7 giant elliptical galaxy. Okay. This is the accretion disk-like thing, and the lavender violet color that you see is the radioplasma. The fire color yellowish orange thing that you see is thermal thing, that the accretion disk that can be seen in optical, UV, or X-ray. The bluish thing that you see, lavender color thing, that is non-thermal plasma that you see only in radio, like GMRT. All this thing at the very center with the highest resolution possible. If you image, then you will see the Event Horizon Telescope's image. How small You can see 50 microsecond. Various thing now. This is that picture, famous picture. We are lucky to be living in this era. So that is at the very center, from which, from this accretion disk at the center is the black hole, and the plasma comes out. Remember, it is quadside radius from which nothing can come out. So the jet comes out and goes very, very far, goes out of the galaxy. This is the non-thermal plasma jet you can see. It goes very far. Okay. That is what is, we have to have this picture in our mind. That from very center of this galaxies, the plasma comes out. Okay. There is one more point you need to understand. That was M87. One more point is the magnetic field is very important in this system. So let me show you one more picture where a strong magnetic field case, the weak magnetic field case has been hydrodynamically created. Okay, magnetohydrodynamically. The white lines that you see worm-like thing, there is a magnetic field line representation. This is simulation, no animation. So top one is the strong magnetic field case. The bottom one is the weak magnetic field case. Okay, what you see, the plasma, electron and positron and proton, they go around, they gyrate around the magnetic field lines and get guided and come out of the galaxy's gravity. Because they are relativistic, they no longer care the gravity of the galaxy. Few hundred kilometers, few 1,000 kilometers enough to come out of the galaxy. And this cosmic relativistic moving, 10% speed of light almost, they go in the magnetic flow, following the magnetic field lines. They go far out of the galaxy. You have seen this picture now, much farther than. But what happens to the lower magnetic, weak magnetic field line? They dance around. They are not that stabilized. They are not energetic enough to go out. They move left, right. The precise kind of thing get disturbed. That's too much, and they create kind of non-thermal bubble, small size bubbles, mushroom size bubbles. Unlike the top one, which is with a proper head, it moves much farther. So this is going to lead us to understand what is happening in weak cases, bubble cases, and large lobe, giant lobe cases. Okay, this is a very recent one. So we will have a understanding of this code. The center of the galaxy, almost all large galaxies, there is almost a black hole which is sun based, is active. Jet comes out, which can be seen by a radio telescope. Sometimes it just comes out and hits the galaxy. When it goes, if it's a strong magnetic field case, it goes out of the galaxy, goes much, much farther. Okay, let's move. Okay, so this is a galaxy you can see here, which is not forming star, not looking blue, it's looking reddish, yellowish. So this is a post-star burst phase, no star formation happening there. And from the same object, I have shown the radio picture in bluish contour here. That's from the same galaxy, radio emission is seen on the top and at the bottom. Diffuse, faint, not so strong. What has happened? It should have been created by this kind of lobe, strong magnetic field plasma jets, but this is diffuse now. Some time back, somebody was smoking here, like diffuse. It has dispersed in the intergalactic medium. So we should understand this kind of object. To understand this kind of object, post-star burst plasma from these galaxies, you can create an image. You can make this kind of image, red, green, blue picture. Red here is from GMRT image, blue here from VLA in USA, very large array telescope. Post-star burst galaxies at the center. So if you can make this kind of images sitting at your home, you can do it now. If I leave some time and join our Facebook group, in Radiatum Facebook group, there are detailed instructions given there. So this RGB image you can make, red, green, blue image, using NASA Skyview web tool, following Radiatum guidelines, and start understanding this kind of plasma outflow from galaxies, how galaxies are being affected by this plasma outflow, and how galaxies are changing because of this outflow from this black hole accretion process. Not only it helps your understanding, it is going to help scientists understand their research process. So this plasma is very quickly, I will going to show you what is what kind of radiation process from this plasma. Suppose it is a magnetic field, this charged particle electrons or positron, they gyrate around that in a relativistic speed. When they do that, then the radio wave comes out. It is not thermal emission, not bell-shaped, not black-body behavior, not Planck's law. It is non-thermal synchrotron plasma. Each particle there will be radiating in a way like this: log of flux, log of frequency. They have a peak and they less on higher frequency and lower frequency. If you have a collection of particles and they are different, not like following Maxwell-Boltzmann distribution, but they are power law following. There's a large number of low energy particles, very few high energy particles. Each of them will be behaving like this. So from this collection of these particles, non-thermal plasma, you get a added of behavior that at low frequency you get lot of flux, you get high, you get little flux. These are high energy radiating mostly. These are low energy particles radiating mostly. Remember, all of them are relativistic plasma, magnetized relativistic plasma. So once black hole accretion process create this kind of thing, suppose then it doesn't create, it doesn't launch plasma for some time. What happens to that plasma that is hanging in the space? That plasma, which is having this kind of slope of radiation flux, frequency, low frequency, high frequency, it is going to have a power law slope. I have described you this power law slope, log plot. This slope is going to change with time because rate of energy loss is proportional to the square of the energy of the particle. So at high energy, they are losing energy at a higher rate. So this fluxus is going to vanish at high frequency faster. So with time, the straight line slope is going to get curved. With time, cooling by radiation loss, you can solve. The non-thermal plasma that has launched out of the galaxy is going to cool, and that slowly is going to be missing from the high frequency images. It will be seen only at the low frequency images. Suppose here, it was here, it has reached to, it has become lower, which was here has become here with aging, with cooling. Then if suppose limit sensitivity is this much, which are able to detect, now sensitivity remains the same for the telescope, it has gone below the sensitivity limit, you cannot detect anymore. But it will remain this way almost at the low frequency for the GMRT. So sometime plasma comes out, diffuse, stops for a while, then another phase of plasma comes out from galaxies. So this is a GMRT picture. The same color picture can be coded in the contour map. And you can see here the outer diffuse structure in the inner pair. The GMRT image to 240 megahertz, 334 megahertz, 610 megahertz from the Chiranjeev Kumar, our collaborator, his picture. So from the inner, the fresh one will have a straight slope, and the outer diffuse aged after passage of time, the spectrum becomes curved. So from this curving, one can figure out what is the break frequency, where it is bending. Following this particular formula, suppose the time since the plasma is not being supplied from the black hole, the fresh plasma is not being supplied, that can be calculated by knowing the break frequency, where it is curving, bending, at the redshift of the source. What is the redshift? From this formula, one can figure out since when the black hole's plasma accretion process had stopped, or when did this happen at least. So that is the aim of Radiatron. That can we do this kind of black hole activity archaeology and find a smoking since when the was fired, one can figure out. When the gun was fired, if you can figure out, we can also figure out since when the star formation is not happening, since the body, when the body died, basically. So this is what we want to correlate now. So what is the big picture? What are we aiming at now? Okay. So what are we aiming at? We are aiming at geometric like big radio telescope, SCA. We are aiming at 8 big science questions. Various science questions: planet, life in the different planetary system, pulsar, magnetic field in the sun, galaxies and gas in the system, plasma processes, galaxy black hole co-evolution studies, early universe, Big Bang, reionization epoch, various stuff. One of the topic is this: how galaxy star formation and black hole activity have been evolving in our universe. And this, the paper that we published, our image is representing one of the 8 aims of SCA science. You can see in the Vigyan Samagam posters of SCA, one can see the same picture minister is visiting. So this is considered very important. So this black hole galaxy star formation co-evolution process, how it is happening, whatever studies we did, these two findings has been press released by NASA, NRO, Time Magazine, CFP, various organizations. Let's try to understand how can we participate in this kind of studies. So that from India-led science one can do. So this is the picture that the galaxy which is merger remnant, yellow-looking thing. Blue is the star formation seen, young star formation seen in the ultraviolet. Green is the radio plasma launched from the black hole system. I have used SDSS telescope, Spitzer telescope, HST telescope for the spectroscopy, Vela telescope, radio telescope, and the Galax ultraviolet telescope, space telescope. So what has happened in this system that we found that two galaxies have merged. The outer system and inner system are rotating slightly differently. After some time, there is star formation and wind, that the wind blows away. Supernova and O and B type star. Galaxy's gas is removed. The simulation you have seen, AGN feedback. Then the jet comes out. Jet, as it expands, it creates a shock. X-ray heated gas can be seen, and it is going to remove the remaining gas there. So ultimately, the star formation, the little amount of star formation that is happening in this system, that is seen in ultraviolet, will also be over. So this is basically caught in the AGN feedback activity system. Another one. Here, the elliptical galaxy-like thing has two nuclei here, two centers of, because two spiral galaxies have merged there. And what is happening? From a lot of star formation happening at the center, H alpha emission, ionized gas, actually it's million degree or hot gas is blowing out, going up and going down. One can see in spectroscopy. With GMRT, we see the hydrogen gas is also being flowing out from there, seen in absorption. This blue line is the GMRT line, absorption line. This is the center of the galaxy. This is the outflowing, blue shifted towards us. It is coming. And with SMA telescope, cold molecular gas can be seen also. That is also being blown away. So when the central outflow is blowing away cold gas, atomic hydrogen, molecular gas, etc., where from the stars will form. That is what is leaving this merger remnant, basically devoid of fuel to form stars, and will ultimately become red and dead galaxy. Not only this can, even spiral galaxies, normal spiral galaxies, almost all of them have million solar mass black hole. They also create this kind of jet. One can see here, this is a nearby spiral galaxy with TGS as GMRT and NVS as VLA. One can see this jet coming out. There's another study. This is the picture of the
Just stay online. There's some technical problem at the speaker's end. He'll be reconnecting. Just stay online. We'll be on soon. You can post your questions here. In the meantime, Dr. Ananda Hota logs in. We'll collect the questions and we will uh, he'll finish his talk and then address to your questions. In the meantime, you can post the questions here.
Yeah. Can we go now? Please share my screen. Yes. So I was here that yes, we were looking at a small tiny radio bubble at the center. So one can see that this is spiral galaxy, but then in radio waves one can see a small bubble. That same radio bubble seen in contour can be also seen very hot in X-ray. From Chandra X-ray observatory we observe. So what is actually happening? That we are seeing the radio plasma coming out from the black hole accretion process is going to push, heat, blow the gas in the spiral galaxies as well. So as you have already seen in the simulation that there are large jets with strong magnetic field goes out of the galaxy. There are small scale radio bubble like thing just now you saw here, bubble like thing going to heat the surrounding gas. So the large jet case is this, that from the small galaxy at the center one can see the plasma going out, and long back when it was released that dispersing and diffusing in the space. This is discovery in exotic galaxy Speca. First, probably the first international news making discovery from GMRT. Press release by NRO, NSF USA, NCRTFR, Royal Astronomical Society UK. You'll Google it. Very famous and interesting case. I will describe you. So it is not just one case of plasma coming out of the galaxy. It's one episode, two episode, probably three episode has happened. And the outer one is megaparsec size. One parsec is 3 light year roughly. So millions of light year size. Okay, and the central one is unusually a disk galaxy, not elliptical. Okay, so you can see here the disk galaxy plasma, and the fresh plasma is coming a proper shape, compact, bright one. And the old plasma that was dispersing, diffusing in the surrounding is the distorted, faint, and irregular shape. I told you before that we look for this kind of faint and fuzzy things, and that is what is we can do it. So we will look age date star population synthesis. We'll figure out the date of the star formation in the galaxy. We'll figure out the age, smoking gun, the relic of that smoke, how old this plasma is from this spectral aging process. So our purpose is to detect that kind of faint, fuzzy, irregular plasma with GMRT. Okay. So with this Pekka galaxy, with my MSc student, hello, again, yes, again failed. Okay, I'm trying again. Bye. Bye. Hello.
As well. So you continue.
Yes, yes, I am fine actually.
Yeah. So you go on.
Yes. Hello. Sorry, there was a misunderstanding. So you can see you. Let me go full screen. So you can see the evolutionary history of this galaxy has been interpreted. How far the galaxy is? Galaxy is very far. Light has taken certain amount of time. Star formation happened. After that, the radio galaxy small lobe came out. After that, the lobe grows. After it is growing too much, the second episode jet comes out. The older plasma is distorted and big. The third episode has come out. So we are trying to understand the star formation history of the galaxy. We're trying to understand the AGN outflow of the galaxy. Okay, this is what we are going to say. What is this object saying? Is that in this central galaxy, the merger did not happen. Merger did not happen. Whereas almost all galaxies that we knew that till that day in 2011, that the galaxies merge, they become an elliptical, they have a lot, much more massive central black hole at the center that creates this large plasma jets. This was the first clear case that the central galaxy is not an elliptical. Central galaxy did not go through a major merger. If that is the case, are we seeing a different kind of galaxy? Possibly, this kind of galaxies are rare in the nearby universe, but probably it was more common in the high redshift early universe. So the question comes in, we are exploring this process, that are we seeing Speca-like galaxy, the first massive black holes and first massive spiral galaxies? After our discovery, actually, 5 more cases have been discovered. And this is very interesting and growing field now. So to understand all this thing, we need to use all telescope, optical telescope, SDSS survey data, HST, this WISE ultraviolet data, infrared Spitzer, infrared WISE telescope data, the new WISE comet that was discovered and made a lot of news because of this telescope. And this is CFHT, our own GMRT, our 3.6 meter Devastal optical telescope. This is yet to I'm yet to observe with this. This is our XMM. This is CFHT. This is this is Subaru telescope, Japanese telescope I have used to observe Speca. This is VLA, and this is subliminary molecular line. This is our AstroSat. So we have to use all kind of things because only then we can understand the star formation history and the AGN history together. So India is part of a lot of these mega science projects. Mega science projects, you all may be knowing, we are spending millions, hundreds of $1 million into these big projects, and that is how actually we all are part of it. Why are you not taking due advantage of it? We should take due advantage. How are we going to see? Our GMRT is already the largest of its kind, I have told you. So compared to all the SCAR telescope that is being built, LOFAR here, and all other radio telescope, their size, collecting area, bigger is always better in telescope size. We are big. We are largest, as I said. So why are we not using it? I have already described this thing. Our TGS survey is best, lowest frequency. Remember, low frequency is better because we can see the old relativistic plasma. We can go further back in the history of the black hole activity. So highest resolution, lowest frequency, we are the best to detect the black hole's history, activity history. We have the best, so we have to use it. So how you use? The first step is to make this kind of red, green, blue, optical, radio, ultraviolet, infrared, this kind of RGB images. So first thing you will be doing after entering Red at Home Facebook group is this. Make and understand RGB contour images. This optical with GMRT contour, UV optical IR RGB image with GMRT contour. GMRT TGS survey data has been put as contour there. With another VLA, one we combine red, green, blue. So this is red, this is blue in a optical radio picture that we make. What you see here is radio jet, and the X-ray is seen in blue. One can see that when the radio comes out, it hits the surrounding medium to million degree Kelvin hot gas, so that becomes X-ray hot. That is what we are trying to understand. The jet comes out, how it interacts with the host galaxy, how it goes out of the galaxy, what is their outflow history, basically. So this is also I'm repeating now that I teach from home, you learn at home, you discover from home, astronomy at home, you discover from home, we propose to GMRT, we collaborate with many professional astronomers, you become part of the GMRT proposal, co-investigator there, you get trained in various institutes, we work as an inter-university nationwide human resource collaboration. Using GMRT, we publish. You become co-author because you discover. There will be professional astronomers as your co-author collaborators. So how do you train? That's what. This is me. This is Ranjip Konar. We were doing this Red at Home Discovery Camp in International Center for Theoretical Sciences, Bangalore, which is part of TIFR, Tata Institute of Fundamental Research. 15-20 people I trained for 1 week. How to make discoveries using GMRT data. Once you discover, you become part of the proposal, as I said. So you become part of the proposal. Which proposal? The ongoing project called GoodRAC, GMRT object discovered by Red at Home Astronomical Laboratory. You join my. This is how you become. See here. This is our proposal. In the NCRA TIFR, which has built and runs GMRT. Their website. These are all citizen scientists, Red at Home member. These are professional collaborators, Chiranjeev, Stalin, and me. When your object is being discovered, you can go to GMRT and observe. So you become part of the real observation. Red at Home discovery is leading you to become an almost a co-investigator in the GMRT research. This is how you publish. All of these people are non-PhD degree, non-researchers. This is what's so interesting that public need to be part of it. Like this current talk, you also get trained in 1-day programs. 1-day program where you get trained a little bit how to understand, make RGB images, how to understand them. In 1-day program, if there is a available, now it is happening online, 100 people can be trained simultaneously. So this is what the I have already described also. The leaders like Dr. Ratnasri, Chiranjeev, like my collaborators, Shravani Baddi, etc. One of the person is also Priya Hassan, who introduced me. We are collaborating to make publications. You become RGB image analysis analyzing member. These 150 people that I have trained for week in discovery camp, they are going to help you, and we will publish paper. So I'm going to show you a few successful stories. How sitting in that discovery camp, how sitting at home, people discover, and we observe this thing. This is what was looking like, not looking like in standard radio galaxy, looking curved and crazy, like distorted shape. We're not sure what is this. Silpa Dubbal found this, and we observed with GMRT. This is what is the picture. At the very center, you can see the host galaxy. You can see tiny lobe coming out. The, and the much larger region, you can see the diffuse distorted thing. One can understand there black holes history, what it has been happening. Another one from Sayarun Dharmik from Hyderabad, distorted looking shape. When you go deeper to understand, this is blue is VLA, red is GMRT. You see it crazy. This is the host galaxy, but there is no jet. The galaxy has moved or the plasma has been shifted. This is the moment you find this kind of old plasma, your chances of connecting it to the star formation history is better. Because star formation has happened, one can see star formation history for several billion years actually. But plasmas are only few 100 million years at most. Another one from Orpita. This was not very sure what is happening. So we looked at with GMRT. We found, see, the black hole's jet axis has probably changed from earlier it was something else, now it is something else. Or maybe some other process happening we don't really know. Another one, the Pratik Dabade, who is about to finish his PhD in Ayuka with Netherlands Leiden University registration. So here the plasma is coming out of the galaxy, but the lobes are bent. How this is bent with much detail one can find out. This is roughly only this much one can figure out. Some diffuse emission, peak, and the host galaxy. Here one can see much finer details. Probably episodes and diffuse thing. One can see their black hole history. Another engineer by profession now, who found this object. And he is part of that. Is why actually one to study with which part of this paper. Another one, a very diffuse old plasma. It is not from the galaxy, but from the whole cluster. This is what is an identity of GMRT almost. You can also make this image. When you observe this thing with GMRT, you can see the very sharp filaments, the magnetic field relativistic plasma in this hanging around, orphan plasma in this clusters of galaxy. So with this thing, basically, you get all this head-on that you make, all the progress that you make in your astronomical project involvement, you get recommendation letter. You get selection to your PhD project. Arpita, Sagar, what is his name? Sumanta. They are from Orissa. There is no astronomy research institute there. They get involved doing a small project with me through Facebook, this kind of online class. So almost 25 of them out of the 150 people that I've trained are doing astronomy MSc or astronomy PhD in foreign land. There are many in India also. So this is how boosting your career. I not only get you to meet father of Indian radio astronomy, I'm involving you to be part of the research, recommending you for your career growth. That is how this Red at Home Astronomy Collaboratory is a real collaboration between you and me. So Professor Govind Swarup, who has led the building of GMRT, he encourages me from the very beginning. Dear Ananda and Red Group, he is always encouraging. You can see his letter. Thanks for the letter from Sagar Sethi, who lovely picture we made. My best wishes for astronomers at Red Home. Now the TGS's images are available. Red Home astronomers should hurry up and find gems in those images. This is my PhD guide, now leading the online teaching from Ayuka. Okay, I'm almost coming to the closing of my talk. Developing scientific temper, humanism, and spirit of inquiry and reform are enshrined in the Constitution of India. And citizen science projects are the important component in working towards that goal. Red Home is a significant citizen science project which has touched many parts of the country and enthused young students to take up scientific projects in astronomy. It has also helped expose them to one of the most powerful radio telescope, GMRT, built and operated by NCRT-IFR. I wish Red Home all this success in its endeavor. The ICTS founding director, ICTS-TIFR actually, it is a platform for new initiatives. For example, you are here. I think this Atom Collaborative is a new initiative of so many people to be looking at the astronomical data and leading to some science out of it. So we have provided the platform. Wonderful thing. He was acting director in Indian Institute of Astrophysics, Professor Jayant Murthy. India has large number of students and even office goers who are excited about space and astronomy, but have not had opportunity to pursue their passion. Groups such as Red Home provide such opportunities using publicly available archive from worldwide astronomical community. Using archive, Priya Hassan and Najam is also teaching students how to do that. This is very important to be part of astronomy. It's a unique culture. No culture, no science probably had this kind of open culture, open to sky culture. It's a slight personal praise also. With everybody knows Professor Bala Iyer because of leading role in the gravitational wave discovery. Starting in 2013 and mentored solely by your personal passion and vision, Red at Home has grown into successful citizen science initiative in India today. It has supported intellectually hungry undergraduates and graduate students and amateur an opportunity to do research and contribute to exciting discoveries in astronomy. It mines the excellent data of GMRT and spreads the message of how science works to a works to a larger population in the country. I hope your effort will serve as a model for many branches of astronomy and science. Wishing you all the best. Keep up exciting work. So, looking forward to your participation in citizen science research. Big data problem can become a big prospect through mega science projects like India is participating in and citizen science. Research and development all can happen at home. It is our social responsibility actually. So let's join hand. So at the end, I will give you a flow of work. Join at home Facebook group. That is our starting point. Read the notice board or the first or pinned post in the group. All the steps are described. Make RGB contour maps using NASA Skyview and post images there. We'll start discussing there. As I said, there are many e-astronomers, trained citizen scientists who will discuss with you, and I will also come. So this is participating in those making RGB images and posting. It's called Daily Galaxy RGBC. Follow rules, get RGB qualified, and get selected as an astronomer. You will get trained for 7 days or even online now. So there you will be joining the Dilse discovery. How do you discover objects from GMRT TGSS data? Be co-investigator in GTAC approved GoodRAC. Once you discover something, we will put that in the proposal. Be RGB analyzing trainer. You are senior now, you have discovered already. Train others people. So this hierarchically, people will grow. Like in 1 day program, I have already trained more than 1,000 people. Now it's online mode, it will be going to several thousands soon. Be co-author in conference paper, international journal paper. Grow in your career. Contribute to national growth by discovering from GMRT. Of course, science is our aim, astronomy is our aim. We will be using GMRT, which is our world-class facility. We have to take advantage of that. And the other factor that we have to take most advantage is we are all young nation. Largest number of young science and technology trained people connected to internet. We have to lead. This is our necessity because we are paying for all these things. It is our duty, fundamental duty in the Constitution to do excellent work in whatever field we are, alone or in a collectively in a group, so that nation progress, nation goes ahead, nation leads. Thank you very much. Thank you.
Thank you, Ananda, for a lovely talk. And as an advice for all the students, Ananda is doing excellent work. Many students have benefited tremendously from his rad at home, so you should join him. Many of the questions which were posted, he has answered in his talk regarding how do we learn RGB analysis and so on, which he has said. We are left with very little time, so I will post just a few questions. Here's one,
Okay.
Another. So Gitanjali asks, so when you say mass of galaxy increases, you mean only visible mass or mass of visible plus black hole?
Okay. When I say mass of the black hole increases, it naturally means the black hole's mass is increasing by accretion or the AGN activity. And because of star formation, the stellar mass of the visible mass of the galaxy is also increasing. And indirectly, very little though, the curvature of the galaxy is also increasing. This curvature process, H1 is seen to be falling towards the elliptical axis, merger imminent continuity. So everything is actually increasing. It is only matter of which mode you are acting in it. H1 always star formation, visible mass is increasing, AGN activity, black hole mass is increasing. I can
Uh,
come and answer there also later.
Vishal had asked how can we take part in this kinds of project. I think Ananda has already mentioned about it, but you want to say something specifically? How
See,
can
this
we
is
take
very
part in?
simple actually. Okay. You simply just join this Facebook group. From there, your journey starts. If I am not available, there are plenty of students who are going to help you. The moment you make an RGB image, your understanding of a radio galaxy emission, multi-wavelength image of a galaxy starts actually. Describe the structure and color. From that RGB image analysis only, your journey starts to become a co-author in the MIT-driven research paper. As simple as that.
Here's one. Vandana Singh asks, are the colors like red, green, etc. convention for different wavelengths?
Yeah. To have a color convention with some physical meaning, we have set up a rule that anything looking red has to be bright in long wavelength. Anything looking bluish has to be bright in short wavelength. This is physically meaningful as long as thermal emission, or physically meaningful as long as both the red and blue are in the non-thermal emission. So once you join the RGB image analysis, you will understand details. This only have three colors with the one contour. So it is confusing, but next.
Yeah, so okay, I think we'll come to the end of the program. Thanks for being with us, Ananda. It was a lovely talk, very inspiring, and you've been doing wonderful work. And I encourage students
Thank you
to
very much.
join.
Thank you
Thanks,
very much.
thanks.
Yeah, students are our power. They love astronomy.
Yes, thank you. Goodbye.
Welcome. Thank you very much. Thank you, everybody. Bye now. See you on Facebook or in YouTube comment that I will come sometime.
Yeah, and obviously we
Okay.
thank Ratna Shri for her support and
Yes. Thank
organizing
you,
all this.
Ratnasri.
Thanks
You
a
are
lot, Ratna.
listening. Thank you.
Bye.